In this video, we're going to formalize our idea of computing products of complex numbers by using what we're going to call the polar form. This will also be a gateway to the complex exponential that some of you may have seen or had hinted at before, but this is also going to be a way we're going to look at vectors in the second term with APSC 172, so it's worth seeing for its own sake. The idea behind the polar form is that if you have a point or a vector, you can reflect it in coordinates such as the x-coordinate and then the y-coordinate, or alternatively, you can define that location by an angle, which we are going to call the argument of the value, the argument of the complex number, or argz in short form, and a magnitude, which we define by the absolute value, again indicating size. Notice that the angle is going to be in radians, as any good calculus angle is, and it's measured in, fortunately, the same way we'd measure regular angles for cosine sine, counterclockwise from the positive real axis. And again, we just define that angle as something called arg of z. Once we do that, that means we have two alternative forms. We have the Cartesian form, where we represent a complex number in terms of a real part and an imaginary part, or a real component and an imaginary component, and alternatively the polar form, where we list off the magnitude, then this little angle symbol, and then some number representing the actual angle for our vector relative to the positive real axis. To help us get started, we're going to translate from our commonly used form, the Cartesian form, and turn it into the polar form. Now, honestly, the easiest one of the two operations is to figure out the magnitude, and this is just using Pythagoras. If we have a vector, the length of that vector is the sum of the two sides squared, then square rooted, just like a regular vector. So here we'd have minus 2 squared, and again, we're just taking the coefficients. So it's negative 2 and positive 2 without the I squared. That's how we would draw that out, thinking of this like an x component and the I indicating the y component part. So if we keep going, we would have the square root of 8. Now the angle, or the argument, is something that usually takes a diagram, at least in my experience. If we're at real axis and imaginary axis, and we're at negative 2 for the reals, plus 2 for the imaginary component, that we can pretty much observe because it's symmetric on both sides here. We're going to have the argument of z is going to be 3 pi over 4 in radians. Remembering pi is a half rotation, and we're 3/4 of that. What our summary is that z1 then can be written as the square root of 8 with an argument of an angle of 3 pi over 4. All right, let's do some other simple ones. Let's take the imaginary number I with a negative sign in front. If we find its magnitude, again, it's helpful sometimes to write this out in full Cartesian form. So it's 0 real plus a negative 1 component for the imaginary. And so we'd have 0 squared plus the negative 1 squared. The I does not play a role when we're calculating magnitudes because we're taking this coefficient or this component and this coefficient or component and squaring each of them by themselves, adding them and taking a square root. And so we get the square root of 1, positive 1, and so we get a magnitude of 1. Notice by the way we're doing this, the magnitudes are always purely real numbers. That should be emphasized. We're never going to have a complex number as the magnitude for these polar forms. All right, what about the argument? So we'll do a little sketch again here, and this point is negative I, so our real axis, imaginary axis, it's minus 1 in the imaginary axis. So counting counterclockwise around here, that would be 3 pi over 2 for the angle. And so our z2 here is 1 with an angle of 3 pi over 2. That is our polar form for that particular point. Just clean up the angle notation there. There we go. Much fancier looking. And last but not least, what if we have a real number? So this is interesting because it does change in a way we might not initially expect. First of all, the magnitude is exactly what we would have expected for this negative value here. It's like an absolute value. How do we see that? Well, we're going to take negative 2 squared, add it to the imaginary component squared, and that's going to give us a positive number underneath, and that's going to be equal positive 2. Then when we do our sketch of the position, we're out here at -2 on the real axis, and so when we do the angle, we're going to get an angle of pi. So the negative number 2 in polar form is positive 2 for the magnitude, but with an angle of pi. That's the polar form for that number. Now we just remind ourselves, one of the reasons we look at the polar form, besides we never know what we're going to do next, but in particular we have the rules for multiplication that work nicely if we have the polar form. So here we have Z1 in Cartesian and its polar form, Z2 Cartesian and polar, and if we take the Z1 times Z2, remember the rule we're going to use is multiply the magnitudes, and we're going to add the angles, or sometimes called the arguments. What does that look like here? That's going to be the square root of 8, and then the angle, here we did it as negative pi over 2 plus the 3 pi over 4. I'm just going to put that in brackets here. 3 pi over 4 plus the negative pi over 2, all of that together is going to equal root 8 with an angle of pi over 4. So that was a fairly straightforward process. Let's do the same thing for Z1 times Z3, and if we're not restating the rules, we just take the root 8 times the 2, that'll be 2 root 8, and the argument or angle will be 3 pi over 4 plus pi, and that's 2 root 8 with an angle of 7 pi over 4. Now that seems a little awkward. Don't get too hung up on the polar form. We're going to use it, but it's very much a stepping stone for where we're going in this class. If you think about our multiplication process that we just did there, and noting that we had something about adding the angles, multiplying the scalar values, the lengths, think about where you have seen before a calculation where multiplication is done through adding two things together. If you think about examples like that for a moment, does anything come to mind? Well, hopefully, if you think of something like e to the 2 times e to the 3, how do you multiply two factors like this? Well, if it's the same base, you get e to the 2 plus 3. And that idea is going to inspire our choice for an alternative representation to the polar form, which is using things like e to the 2i, or let's put it in the terms that we're going to see. If I had e to the pi times I and e to the negative pi over 2 times I, if these were my angles and they showed up here in an exponential, well, I would get the sum of those angles. It would be pi over 2 positive when we're done. So it seems potentially we could do complex angle things somehow in this form, and we're going to explore that in the following topic.